So I worked on this framework for peer-to-peer card games. Let's say I wanted it to be a framework in the beginning, but then I decided that I need to test it in a game, but I didn't get to the game part. I just started with the framework stuff. So the idea of this is that a bunch of players get together and want to play a card game online, and they don't want to use a trusted service. So they want to all participate in the shuffling and masking and encryption of cards, and if each one of them should only have access to the cards in their hand and the publicly revealed cards on the table, for example. And I used for this a protocol called the Shuffle Mask protocol. I started reading. I found out about this while investigating like mental poker. This is a thought exercise created a long time ago by the same folks that built RSA. And they described an algorithm. But then later I tried to find something that's a bit better for today's encryption standards, let's say. And I ran into concepts like El-Gamal encryption and the different protocols. Sorry, and I based all the work that I did in this repository on this paper called Mental Poker Revisited, which explains a protocol for partially encrypting and decrypting cards for a card game. And the idea is that every player generates a bunch of key pairs. They share the public keys with the other players, and then they all participate in this shuffling and masking of the deck of cards. And how that happens is they all encrypt every card with the same shuffle key, and then they pass the deck to the next player who does the same. And after everyone has encrypted and shuffled the deck, the positions of the cards are set, and each player then proceeds to remask every card with a card-specific key. And then when the game progresses, if a card needs to be dealt, a player reveals the secret key that they used to mask that card. So if a card needs to be shown publicly, every player shares their secret key, and if a card needs to be dealt to a particular player, every other player shares their secret key, and that player can then open the card privately. And I tried to build the repository as a guide into this study that I did. So I tried to like add a lot of details about how the masking is done, how the cards are represented, and the whole algorithm. So it goes into a bit of math towards the end here. But essentially, cards are represented as points on an elliptic curve. And I was able to use Snarky.js elliptic curve magic to do most of what I did in this repository. And to be able to mask the card, two other points on these curves are needed. A public key that's the combination of all the public keys of the players, and an ephemeral public key, which is a combination of the corresponding public keys to some nonces that were generated during the masking, but these nonces are thrown away. All right, so the way the game should work is that there is a state machine where that progresses through as the game progresses. Yeah, so there's a shared structure which I call like game data, I think, which each player modifies, and then sent to the other players. And then other players are supposed to validate that the modifications were performed correctly and then do their own move. So every move in the game, or every like partial move, let's say, is one of these transitions that need to be validated. So for example, in introductions, every player shares their public keys. And this loop right here represents the fact that that all players need to go around the table. And the same for the shuffling step, the same for the masking step. And then they get to dealing, which means partially opening the cards for the other players and opening the top card, which is something specific for the game that I was implementing. And then this box right here represents the state machine of the game itself, where players need to place their cards on the discard pile according to some rules, and they can challenge each other to like either fulfill the challenge or fail the challenge, or pick multiple other cards. So I think I forgot to mention the purpose of the game is for each player to get rid of the cards in their hand. And the way that it's done is there's always a top card facing up on the table, and players need to place cards on that top card to match its suit or rank. And there's a challenge mechanism that's specific to the game that I was trying to implement, which means that players can force each other to take multiple cards from the fresh pile, making it harder for them to get rid of their cards. Right. So I try to also describe like what happens in this in each step, and how the cards get masked and unmasked and dealt between the players. And then we get to a bit of implementation details, which is where snarky.js comes in, I guess. So my idea originally was that every little transition that is done should be accompanied by a proof generated by a zkApp program. But while working on this, I realized that proofs are very hard to generate, surprisingly. And I think I also have some benchmarks here for very simple proofs, just like comparing three numbers. It takes a while, so it's very hard to iterate, and it also makes the game a bit unplayable if that was a requirement. Like I think this is more than 5 minutes for generating the proof. So it's unfeasible. Yeah, it's not feasible to wait for that for making a simple move. So the alternative to this is that I created this method to check a transition between two states, and I built this method in such a way that it can be run both in a circuit and outside of a circuit. So it's a gigantic bool expression, for example, that needs to evaluate all the possible state changes that are valid in the game. So the reason why it has to be this like gigantic bool expression is for the ability to make it work in a circuit, which means that it has to be a fixed computation. Like every variable has to be evaluated at the same position, every relationship at the same time, and everything. So even when dealing with arrays, and in my game data structure, I deal with a lot of arrays, like the deck of cards, which is an array of structures itself, owners, like who owns each card in the deck, players themselves are like a collection of arrays of keys that are each specific to each card in the deck, and player secrets, where like when players open cards, they publish the secret corresponding to that card, and so on. So all of this needs to be evaluated in these transitions. And I discovered that state machines plus circuits are hard, mostly because normally when you build state machines, you have these like shortcuts that take you out of a state that's invalid to evaluate at that point. But because we're in a circuit, every possible state has to every possible transition has to be evaluated at the same time to compose that big result. And this means that even states that don't really make sense need to be evaluated every time. So like even when there's no cards in the deck, just players introducing each other, it still has to evaluate that the transition doesn't affect the deck or something like that. Okay, so maybe I should show some code at this point, or oh yeah, yeah. The rules of the game is, if anyone's interested, this repository at this point implements, I think, up to this point. So just dealing the cards between the players, shuffling the deck and dealing the cards between the players. But the way I structured the code is that everything is done, everything is checked in tests. So it's like every change that I make to the game data or game transitions always gets checked. And it's also like checked in automatically in the CI test run for every transition or every PR that I make. All right, so yeah, the game data is like this structure, and it has to be modified by players at each turn and then validated. The modifications are like these game actions that each player does. These are not necessarily circuit friendly, let's say. So I took some shortcuts, like, I don't know, like making JSON transformations and stuff like that. I know some of these could be made circuit friendly, but since the players are not proving that the actions they make are valid, only the transitions that result, I was able to do this. And then every transition needs to be validated. This means that I have this gigantic is valid transition method, which is a collection of assertions essentially, and adding it all to a result that happens at the that should be true at the end. In testing, these things break earlier, but I also checked that the method runs in a check computation as well in one of the tests. So yeah, I don't know if I should go into details like this. Maybe it's more fun to show something running. Let's see. Can you see my IntelliJ?
Yeah.
Awesome. Okay. So the way I have it set up is that I'm able to start a server, oh, not a server, a node with using like peer-to-peer networking. And this server creates a game and broadcasts it to a channel. And then other players can join and listen for existing games. And once a game is found, players join and they automatically start shuffling the deck. So what you'll see here is players finding each other, like this player here and this player here finding each other, and essentially progressing through the introduction, shuffling, masking, and dealing of cards. And yeah, so every player checks like where they are in the state machine, and if they are allowed to make a move, and if it's their turn, they make the move and publish the move to the channel. So for example, this is the second player, let's say. So last move was, in this case, last move was masking. Continuing means that the previous player was masking cards. It's my turn to mask cards. I'm continuing to mask. And in this case, it looks a bit different. So yeah, it just says like when it changes state, because it's the first player that initiated this. And at the end of all the protocol, the player is able to decode the cards in their hand and the top card, which is visible to all the other players. And so should this player, if nothing crashes. Yeah, so let's see. Hopefully the top card is the same. Something crashed after it. But every player is able to see the cards in their hand and the top card, which in this case is the same. I mean, it should be the same every time. Then. Yeah, I hope you got the point. So from this point on, the game, the project should progress with like players actually playing the game. So picking the card in their hand and uh, dropping it on the discard pile and changing the top card. Yeah, and as I was saying that everything is done in tests as well. So all the test passing can be seen here. It takes about 40 seconds to do it while not using proofs. So I think that's about it.